Okay, now in mechanics, we used the conjugate momentum to define the Hamiltonian. For a single particle, the formula for the Hamiltonian, it was P Q dot minus the Lagrangian L. You know what P is in terms of Q, and you also know what the Lagrangian is. So you just simply plug this in. It's an exercise that you've done before. And this was equal to E squared over 2m plus V of Q. And remember, this is the answer that we got previously. And it just shows us that the Hamiltonian is nothing but the total energy of the system. Good. Okay. Now let's work out what is the Hamiltonian for the n particle system. Well, again, we're going to get the total energy. The energy will be a sum of the energies for each particle. And for the eighth particle, HA will be equal to PA Q dot A minus LA. And again, you know what PA is, and you know what LA is. So just plug it in. This is very similar to the single particle calculation. What you will end up getting is PA squared over 2MA plus the V of QA. And this is great because this looks like the kinetic energy of particle A plus the potential energy of particle A. And then the total energy would just be a sum of each of these energies. Good. Okay, now let's try to generalize this to field theory. So in the same way that HA is something for the eighth particle, we now want to write down something that we'll call the Hamiltonian density. And this will be at position x and time t. It depends on position x because HA depends on the label A. And what will this be equal to? Well, here it was the conjugate momentum times by the derivative of the coordinate. So we will have pi x of t times by phi dot of x and t, and then minus LA, which for us is minus the Lagrangian density. And then the generalization of the second formula is that the Hamiltonian will be equal to, so the sum over A, well, the sum over index A becomes an integral over d3x, and then we will have H sitting there. So this justifies the name that I was using. H is the Hamiltonian, so clearly curly H here must be the Hamiltonian density, okay? And you can see how I'm generalizing these formulas the whole time. Every time there is an A dependence for the n particle system, it becomes an X dependence in the field theory. Good. So this formula for HA had no sums on A, so the formula for the Hamiltonian density has no integrals in it. It depends on PAQ dot A, so it'll depend on pi at x and phi dot at x. Now, what was the Hamiltonian picture good for, the Hamiltonian description of classical mechanics? Well, it was good for quantizing. And what we actually did is we promoted the Poisson brackets to commutators using Dirac's correspondence principle. So let's just remind ourselves of what the Poisson brackets were. Well, we had Q, comma P. The Poisson bracket of Q and P was simply equal to 1. There's a natural generalization of that for the n particles. The Poisson bracket of QA with PB will be equal to delta AB. So the coordinates will Poisson commute if they belong to different particles, and otherwise it'll be delta AB when it is the momentum and position of the same particle. You just get a 1. Now remember what the formula for the Poisson bracket was for the single particle case. We said A comma B was equal to, there were two terms. It was dA dQ dB dP minus dA dP dB dq. And let's just be completely explicit on all of the rules for the calculus. dp dp was 1, and that's the same as dq dq. And then we said dp dq is 0, and that is the same as dq dp. And this is all of the rules that you needed to go ahead and calculate Poisson brackets. For the case of n particles, what is the Poisson bracket? Well, the Poisson bracket between A and B would be equal to, now we would have a sum over the n particles, and we would have dA, dQA, dB, dPA minus dA, dPA, dB, dQA. And what were the rules of the calculus in this case? Well, dPA, dPB would be delta AB, and this would be dQA, dQB. And then dPA, dQB, well, that's just 0, and it is equal to dQA, dPB. So those are all of the rules that you need. So let's now start to write down the generalization to field theory. And the first thing that I want to generalize is this formula for the Poisson bracket itself. So what would we get here? Well, it would be the Poisson bracket. We want the QA, so this is going to turn into phi with an x, comma t. So the Poisson brackets are always calculated at the same time. Then we've got PB, so this will be pi, and we want an index, but notice we went from index A for Q to B for P, so we want a different index. So we'll put your y, comma t, okay? And then this should be equal to, well, it was a Kronecker delta of AB, now it will be a Dirac delta of x minus y. That's how Kronecker deltas generalize, they become Dirac deltas. So that is now the Poisson bracket for the field theory. And I hope you can see that I just keep using this rule that I need to generalize the discrete indices to coordinates. Next, let's generalize this formula for the Poisson bracket. Now, in this formula on the right-hand side, so let's start off, let's write down the Poisson bracket. Oh, stop doing that. The Poisson bracket of A with B. So what is this equal to? Well, we've got a sum over A. So this is going to be an integral d3x. Then we've got a derivative of A with respect to QA. So now we will have a derivative, and I'm going to have to spell this derivative out. It's something called a functional derivative, but let me just write it down for now, and soon we'll generalize it. And it must be evaluated also at A. So we're integrating d3x, so also at x. And then we've got a derivative of B, again, a functional derivative with respect to the conjugate momentum, again at x, minus, and now we differentiate A with respect to the conjugate momentum, x and t, and we differentiate functional derivative of B with respect to the field at position x and t. So that's now the Poisson bracket. And let me just say this one more time at the risk of boring you. The sum over A has gone into an integral d3x. I had a derivative of QA, a derivative of PA. So I'll get functional derivatives of the field at phi x and functional derivative to the field pi x. Now, I haven't spelled out what those functional derivatives are, but I will do that in a moment. So we'll continue in a moment.